think we're recording now. Okay, so next up, section 3.2. It's all about big O, okay? Now, before we even begin, I'd like to collect some information from you, the ideas, your understanding of what the following terms mean. Now, we'll be using and reusing these terms in what follows, and we'll give precise definitions for most of these terms. But before we have the definitions and the precise sense in which those terms will be used throughout, I'd like to collect your notions of what those terms mean. You've certainly come across those terms before, and you must have formed some notions of what these mean in your imagination. So let me ask you these questions. And by the way, the answers do not have to be precise, right? Okay, we'll define any of these things. Some of these you know from calculus, maybe others, you know, from other programming courses, CS courses, whatever. What's a growth rate of a function? And for that matter, what is even a function?
So a function is something that you take inputs and you get outputs out of it.
Okay. Okay, so in programming, that's a function. Good point. Anyone else? Well, what are some of the other terms you use for a function, for the word function?
Method.
A method in programming, yes. How about from math classes?
An operation.
An operation would be a term. So how about the term mapping? Did you use the term mapping? How about in calculus when you talked about functions? Those were slightly different, but those were certainly not Java methods, right? When you talk about functions in calculus, what are those guys?
Graphs.
Okay, you can represent a function as a graph. A graph is a particular
polynomial, usually.
It's an example of a function.
Yeah.
Right? So the graph is a representation of a function, as is a table a representation of a function. So let me see if I have scratch work here. So a function is simply a mapping, right? Another term that you've used, it's a mapping. Use something like a symbol like an F for a function, and that function was defined from some set that you called domain. It could be like a bunch of real numbers, all of the real numbers, whatever. Okay. Okay, you can have a function like this, or another function like this, and so on and so forth. Okay. Defined in some domain. In this case, the domain of the purple function here happens to be all of real. So suppose this is a real line. Again, a graph is just simply one way of imagining a function. It's not a function. A graph is not a function. Yes, we use the language loosely. We'll look at the graph. Oh, that's a function. Okay, true. But it's just the function is a function. It's to use the Platonic term, it's an ideal, right? And then you have a particular representation, way of thinking of the function. It is the graph that you draw or the table you fill out, and so on and so forth. But you have a function. You have this X is what? A domain, a set in which the function is defined. And then you have something called codomain, or okay. Let's say let's make this red, I guess. So you have this Y. Okay, so you have a mapping from this F is a mapping. Okay, so what makes this mapping a function? What kind of correspondence between, let's say here's a correspondence between the elements, some kind. What kind of correspondence would not be a function?
An example would be one input having two outputs.
One input having two outputs. Good point. So if you have like this one input here, and that guy maps here and here, that's not good because you don't know what the value of this function is on that particular input. Is it that one or is it that one? That's not a function, right? However, you can certainly have the case that one element of the codomain is being mapped to from two distinct elements of the domain, right? So you can have a situation where these two guys, this guy and this guy, both map into the same output element, right? That can be it's not a one-to-one function, but it can be a function. what is an example of a function from calculus, let's say? I don't know, something super familiar that maps distinct inputs into a single output.
Area of a rectangle?
So area of a rectangle, good example. That's not what I thought the people would say, but that's good because you could have two different rectangles that map to the same value, right?
Right.
Right. So that's an excellent example. You can have a square that has the same area as some rectangle. That's an excellent example. Two different shapes are mapped to the same output value, a single. What is the value? What's the output? A number, a real number in this case. What's the input? The set of rectangles on a plane. But how about a calculus? That's an excellent example. I like it personally, but I was asking about a calculus function because we'll be drawing graphs in what's to come. So our domain will not be a set of rectangles. Our domain, in fact, will be even smaller than the domains you had in calculus. In calculus, you talked about real functions, f's that mapped reals to reals, like f of x being, I don't know, log of x or x cubed or something like that.
Yeah,
Okay.
one function I could think of is x equals y squared. You have the x mapped to two different.
That's an excellent
values.
example. That's an excellent example, although you said y equals x squared is what you meant. So what you meant is this, and that's an excellent example. So this guy, well, this guy 2 and -2 both map to the same value of 4. That's a parabola, y equals x squared, right? That's what you had in mind. Am I right?
Oh, I thought you were talking about an x value that was mapped to two y values, not a y value map.
Well, that won't be a
Or
function.
sorry. Yeah. I thought you were asking for what wasn't a function. So I'm sorry.
Yeah, so that
yes,
wouldn't be a function, but this would be an example of a function where two distinct values map into one value. So -3 and 3 both map into 9, right? Because that's -3 squared and 3 squared are both 9. Same thing here on the example, -2 and 2, or 1 and -1 both map to 1, and so on and so forth. Now, the reason I bring this up, okay, so we'll kind of return to this notion of a function later when we talk about, in other sections of the class and so on and so forth. But what we'll be concerned here is functions that are non-negative in what's coming up. Why? Because we want the big O notation in our particular context, which is in the analysis of algorithms. Okay, the context of the analysis of algorithms. And when we analyze algorithms, we deal with functions, we'll call them like, I don't know, T of n as time it takes to run a particular input of size n, time taken by the algorithm. Sometimes we'll call f of n. What is f of n? Our x-axis, the domain of our functions, will be actually non-negative integers. You can have an input of size 0, okay, I guess, but all non-negative integers. Okay, so these guys here, this is our n-axis. I'll call it x-axis, call it x if you'd like, it doesn't matter, whatever, it's either n or x. And where our input will normally be an integer. An output will be a real number. So what we're concerned is with functions that are defined in whole numbers. Well, if you want to call them natural numbers, if you want to count like 0, 1, 2, all the counting numbers plus 0 is the set of natural numbers, fine. Call them whole numbers if you want, doesn't matter for us. We're not sticklers for that terminology. To the real numbers. Okay, what are real numbers? The real numbers is, the number of milliseconds it takes to run a particular program, let's say. A program, this f is the runtime of a program. F takes as input an array of length 27, and it takes 3.72 milliseconds to run that procedure on an input size 27. That's our function. So our output, because it's a measure of time, it's the number of milliseconds, nanoseconds, or years to run the program, is a real number. How long does it take? And the input is always an integer. So that's what we'll be concerned with, that those are the functions that we're dealing with in this section of the course. Does that make sense? Okay, so we'll be drawing only the first quadrant here. We won't have pictures like this. Negative inputs do not concern us. We don't care about those. Only positive inputs concern us. And therefore, we'll just draw just the first quadrant here in our graphs. Does that make sense? Okay, so let's just go back to the slides here for a second. Okay, so what's the growth rate of a function? Okay, so it's clear what a function is, what kinds of functions we'll be talking about. What's a growth rate of a function? Let's go through this a bit quickly because we need to get this. Any suggestions? What's a growth rate?
Yeah, I think growth rate is like as you, or maybe I'm just going to describe big and over
that's
like
what I mean.
as the, or yeah, I guess as the input grows, how much how many more steps we're going to have to do on, or how the function grows with the input.
Yeah, exactly. So that's the growth rate for a unit increase in the value of the domain and the variable, right? How much does the value of the function grow as you keep increasing the value? Is there a single measure can you come up in calculus? How did you measure the growth rate? Or in physics, let's say you were describing motion or something. Or
I mean, the derivative? Or
yeah, the derivative is exactly the growth rate,
Yeah.
right? So for a tiny input in the argument, how much does the function value change, right? For a tiny input, okay, you define it in terms of a limit, of course, but okay, and of course that value depends on where exactly you're measuring it, and so on and so forth. So at different points, the growth rate may be different. Okay, if you have a linear function, the growth rate is the same no matter where you look, right? The derivative of 2x is 2, no matter what x is. Okay, so growth rate, fine. How about, what do you mean by an efficiency of an algorithm? Again, these are sort of not the way you think of this. What do you mean by an efficiency of an algorithm?
The relative amount of time it takes an algorithm to complete a certain task, I would say.
Okay,
Like,
so what do you
if
mean?
It takes, like it shouldn't take an algorithm like 20 minutes to solve 2 + 2, like to add 2 numbers together.
Okay, good point.
So
Yeah, good point. So you would, that's actually a good example. You would, if an algorithm takes 20 minutes to add 2 tiny numbers to one another, that you would call that inefficient. Yes. So we have this idea, this notion of efficiency. Any other way that you measure efficiency?
I would guess comparing growth rates of functions.
Okay, so okay. That's a good point. So this is you're comparing efficiency of two functions. How do they compare to one another in terms of their growth rates? If somebody's growth rate is smaller, maybe you want to call it in some sense more efficient than the other who grows much faster. Okay, good point. Any other? So
I would
again,
say number of steps or actions taken by the computer for the
Okay.
program to be completed.
that's another excellent measure, right? So that's another measure of how efficient a procedure is. If you have an input of size, I don't know, 100, and if it takes you, like, I don't know, 2 steps to find an answer, as opposed to 100 steps to find an answer, the 2-stepper would be a much better one, right? Okay, so the fewer operations that it takes, the better, right? Okay. Yes.
It can be slope.
It can be slope. The slope is
When
the derivative that we talked about, right, of the function. The larger the slope, the faster it grows, right? That's a high growth rate. If the slope, again, when we talk about slope, okay, so these are remnants of ideas from calculus, right? The slope is really a derivative. Why do you call it a slope? Because you have a function, you imagine it as a graph, you draw it, you have this particular representation of a function in mind that is pictorial representation. You draw a graph, and there you can talk about slopes. But the more general notion is a derivative, which is really a slope, okay? So because it's easier to talk about it. Yeah, so that goes back to this same idea, right? So the higher the slope, the higher the derivative, perhaps that would be less efficient, because for a tiny increase in the input, you'll have the growth rate is high, meaning that you have the value of the function grows higher. So you want the value of the function, if the value of the function measures the time it takes to complete some computation, you want that to be low. You want that to grow slowly. You don't want that to take too much time. Okay, good point. What else? What do we mean when we say that two functions are equal as opposed to asymptotically equal? What's the difference? Well, what does it mean for two functions to be in some sense equal? There is a sense in which two functions like 4 million or 40 million x squared is equal to 1 over a gazillion x squared. There's some sense in which those two functions
Growth
are
rate?
somehow- sorry?
Growth rate?
Growth rate. Okay. So that would be one measure, the growth rate itself. Do they have to be identical, the growth rates, for us to consider those two functions asymptotically equal?
Now, don't they just have to have values that are equal to one another? So like at some point in the function's growth, they'll be equal to one another, right?
Some point they will be equal to one another. So I don't know. Again, I'm not asking for so precise. You may have a precise definition of some idea in mind, right? So that's not what I'm asking. Okay, so it's a good point, right? So what did you have in mind, just to clarify, so that we're on the same page?
So what I was thinking was like, if the functions are equal, then they're identical. But if they're asymptotically equal, then it just means that that there exists a value for which those functions would map to the same codomain.
There exists there. Okay, so here's a function that is x squared. Here's a function that is x cubed. This is 1. There exists a value for which these two functions are equal. When x is 1, both x squared and x cubed are equal. Are those functions asymptotically equal?
Well, I'm not sure, but that's what I was expecting. But that's what I
Okay,
thought.
no, it's just so we're open now to suggestions, right? So far we're just thinking with these the way we're thinking about these.
Their fixed point are the same.
Sorry, one more time.
Their fixed point are the same
They're
when they just reach the minimum or maximum value of the function.
Okay.
They fix on some value, for example, the both function fixing the same value, and whatever we put as an input,
Mhm.
the value is never changed. For example, 1, 2, 3, 4, the values are different. After 4, the values are the same. We always getting the same answer.
So are you suggesting, so here's one function. Oops. Oh. Okay, so here's one function. Here's another function, and maybe from this point they're all equal. Is that what you're suggesting?
Yep.
Okay, that you would call these functions actually asymptotically equal, but there's even a looser sense. It's a good point. It's a good point that you would consider.
I would maybe two functions that are bound by the same asymptotes.
Bound by the same asymptotes. Okay. Here's sine x, something like that. Here's some asymptote. Maybe they both converge to something. Would that qualify? Okay, maybe in some sense. Yeah. Okay, good. We could continue to sort of like survey people. So what it means, we'll give precise definitions of these things in a minute. Okay. Okay. A couple of last things. The input size. We already talked about this. What is an input size of a problem? How did you measure the input size in other classes? I mean, we gave a couple of examples last time when we talked about sorting. We had the input size for us was the size of the array which we were sorting. That was an input size, the n that we called. What else was where else have you seen problems of an input size, and how did you measure them? those input sizes.
I mean, it could be the the input size of a file.
The input size of a file. What file? So
I
but
mean, like a text file or something. If you're trying to open a text file for reading.
right. So you're manipulating a text file. For example, you want to read it and maybe count the number of words or something. The input size, the size of the text file, the number of bytes it takes to represent the text file itself inside the computer, right? That's one. Or the number of zettabytes it takes to represent like some stuff that you're searching through on the internet or something like that. Well, maybe that's a huge number, but whatever, terabytes, some database, right? That's an input size. How about, like, I don't know, it was an example someone brought up in another section, multiplying two numbers, for example. You know, if you're multiplying large numbers, so how about the number of bits it takes to represent those integers that you're multiplying? That's the input size of the problem. So you can measure it in the number of bits, the number of file size, all these are input sizes, the number of elements in the array, and so on and so forth. So for us, we'll abstract away for these particular measures. So we'll talk about the input size n. The problem has input size n. I can think about the number, the n being the number of bytes it takes to represent the problem, or the number of integers in the array that you're sorting, whatever. We'll have this input size n will always be an integer. Now, let me ask you a question, and I'll let you think about this. Okay, so you have Alice with her computer. And so here's a function t of n. Like they have a problem of size n. You can think of an array of size n that you're sorting. And Alice's computer takes t of n time to sort it with a subscript a, because that's Alice's computer. T sub of a to sort an array, like to solve a problem of size n. Okay, and let's call her computer's algorithm A also. Okay, so that's Alice's solution. Then you have Bob, who takes t sub b of n to solve the same problem. Again, an input size of the problem is n. Okay, and that t is the time it takes Bob to solve this problem on his machine. Okay, measured in, I don't know, years, centuries, nanoseconds, whatever, some time. Now, suppose for a second that Alice's time is much lower than Bob's time to solve the problem. Yet Bob comes back and says, no, my algorithm is much better. Okay, I know that Alice's computer solved it much faster, but mine is much better. My question to you, and I'll step aside for 10 seconds here, and I'll be back while you think about this and see what your suggestions are. Why is it the case? Is it the case? First of all, does Bob have a case to claim? Can Bob say, now look, despite this evidence here that Alice's machine took much less time to compute, the answer, my algorithm is much better. Can you think of the ways of why that might be the case? I'll be back in.
What's popping?
Nothing much.
Yeah,
We're actually
not
going
much,
over.
man.
I'm going over this in another class. So like,
This exact same
facts?
thing right here.
yeah, no, like
Class.
big O data
Oh,
structures.
big O, data structures. Yeah.
Yeah.
Oh yeah.
And was like, oh wow, that's coming back.
Wait, are you
Yeah.
guys? Do you guys have Chorus?
No, I don't.
Oh,
Is that a professor? Because no, I
yeah.
don't.
Oh,
You know.
like ever ago.
Okay, so what's the verdict? Where you guys think?
I believe he can make this claim if his thing is either or the first thing that came to mind is his more flexible. Maybe hers is faster in just this 100, but maybe she can only take 100. His can take 1,000,000. So I maybe his thing can apply to just more cases or something like that.
Okay, so let's okay. So that's one thing. Okay, maybe he's better because, but that would be a different algorithm, right? So remember from our discussion, like from the previous time, from the previous section. So let's say that they both take inputs of the same form. So let's say we gave them the same input, and the output is the correct answer for both of those cases, for both Alice and Bob, right?
Are they using the same the programming language?
Okay, so that's another consideration. Is the program, is this real? Let's say they're using the same programming language as such. Suppose they both wrote,
Everything is the same, right? The computer, the programming language.
okay, so so let's say the compiler and programming language, let's say those are the same, but
Okay, I will say that assuming that the platform is the same computer, same everything, and one of these go with a lower time,
Yeah.
maybe the one which makes lower time is doing a less iteration of over the data to get the answer, and they both get the correct answer, but one is using, I don't know how many lines of program, 20, against the other one that was a little bit more efficient and used only 15, 10 lines of program.
and the one that's more efficient finished earlier. Was that Alice's machine?
Yeah, that
Yes.
was Alice's machine.
Okay.
I was also thinking maybe his uses less memory.
Okay, memory, that's another consideration, right? So that's so maybe Bob's machine took longer but used less memory. Anything else? Okay.
Are they
those are
using
valid.
so the computers could be different speeds, like the CPU?
Okay. Yeah, so that's yet another one. So we can think probably a few others in which Bob has a legitimate claim. So that's yet another claim. Like maybe Alice's computer is a supercomputer. It took her a few seconds to solve the problem while Bob's takes a few years. However, despite Bob's run taking so many years, honestly, let's say Bob has like a laptop that's like from 10 years ago. Okay. So, but Bob's computer may be making way fewer operations. If you gave Bob's algorithm to Alice and she ran it on her machine, then maybe Bob's algorithm would take much less time. In that sense, Bob's algorithm is more efficient. It's just running on a different hardware, right? Here's a so here's what we want to say, that the fact that an algorithm runs faster on a particular machine doesn't say much about the nature of the solution, that the algorithm itself. It says more about the machine. It may be saying more about the machine itself. On a supercomputer, obviously, it will take like much faster to compute, right? Something. If you have a machine that's a million times faster, yeah, it will take faster. Okay, so let me return to that point in like 1 minute from now. Let me recall. Okay, so here's what so last time we had these different problems that we considered. We had the searching problem and we had the sorting problem. And at least with sorting, we considered two different ways of solving the same exact problem. An array of size n, sort the array of size n. We had both a selection sort and we had insertion sort. With searching, same thing. We were searching for an element in an array of size n. We had linear search, and we also have this binary search that we didn't discuss, but we'll discuss it next time after Big O, I guess. Let's return back to those slides. So you have two different ways, and usually you'll have many more, of solving the exact same problem, okay? But how do these algorithms, the different ways of solving the problem, differ is what we need to address. So is selection sort, for example, that much different from insertion sort? Is linear search that much different from binary search? And exactly in what sense? One of you already suggested counting the number of comparisons, and we will be doing this next. Okay, exactly accounting for the number of comparisons. The number of, well, the operations, arithmetic operations maybe. That will give you a good idea of what is the effort exerted by the algorithm. Fine. That effort can be measured either in the clock time, number of milliseconds it takes either Alice or Bob to complete the run of their algorithm, or in terms of the number of operations. We'll measure it in terms of the number of operations, although Alice's computer may be much faster. If they both take the same number of operations, we'll say that in some sense, because they took the same number of operations, despite one's computer being much faster, they're equivalent in some sense, those two algorithms. Okay, because they take the same number of operations and the exact same input.
Will we ever be responsible for like leaning efficiency towards memory instead of time? Like, because that instance is like, you know, the number of operations taking less time, but what if it was the number of operations taking less memory? Like, is there like an
Yeah.
instance in this class or?
Okay, so we'll talk about time efficiency this time. So time, not time efficiency, time complexity, what we'll call time complexity, counting the number of operations. We'll talk about the run times of the algorithms for now. So memory considerations in this part of the course will not be a concern for us. But in general, yes, when people talk about complexity, they usually mean either time complexity or space complexity, but we'll talk about time complexity, right? So we'll be talking about time complexity in what's to come. Right, makes sense, right? Good question. Okay, so again, that time, that runtime, the clock time depends on the hardware and software being used. So Alice's machine is 1 million times faster. It will complete much faster. Now, here's what big O notation is all about. The purpose of big O is to abstract away from all those considerations of hardware and software considerations that the environment that's used to run a particular algorithm. So one of you brought up these questions, very legitimate concerns. Do they have the same hardware? Are they using the same language after all? Because some languages are actually, their implementations are better. So if you run something in C versus Python, you know, they take a very different amount of time, right? So what we want to do is we want to extract the essence of the solution, of the algorithm itself, without worrying about these incidentals, without worrying the hardware being used, the software being used, the environment that's being used to run the algorithm. The sorting problem and the most optimal sorting solution existed in the 50s, several millennia ago, and it will exist 25 millennia from now, provided that humanity will not annihilate itself. And if we still need to solve the problem, the solution, the most optimal solution to the sorting problem will be exactly the same. What will be different is that we will not be using electronic computing machines. Maybe in 25 millennia from now, we'll be computing based on the exchange of our thoughts, for example, or something else, right? So our devices will be very different. Wherein in this speck of history, when we're using these electronic computing machines, fine, we can measure it in some sort of milliseconds and clock time and so on and so forth. But it has nothing to do with the nature of the problem itself. The sorting problem, it transcends the current technology, right? Okay, it was whatever it was in the 50s when somebody found the optimal solution that merge sort is the fastest and proved it mathematically. Mathematical truth does not change. Technology changes. So what we want to get to is we want to get to the essence of the solution to a problem, the mathematical essence of it, the heart of the problem, as it were, abstracting away those details like hardware and software that's being used to run the problem. Okay, so I'll talk about these lower order terms in a minute once we get into the examples. But all of this. So let's start with this. Let's stop with with this introduction here, because we're spending too much time on this high-level overview. I think people are kind of like, does all of this make sense? This is like more than 30,000 feet. It's like this is like overview from like the stratosphere of what the big O is all about. Right. So now we'll have to be a little bit more concrete, right, about big O. So let's get started with the definitions. Any questions so far? So now we'll actually do some math, right? So more interesting things. I want to give you the definition. The purpose, we want to have this clear language, very precise language in order to think clearly about these problems, okay? So what we want to define is what it means to say that, actually, you know what, let me go back to slides here. What is that? Oh yeah, we just drew this. These are the same slides, I'll post them later. So here's our slide. What we want to do is say, what is what do we mean to say? What do we mean when we say? So what does it mean to say? What does it mean to say? And what do people mean when they say that f of n, again, remember our non-negative functions, is big O of g of n. So we have two different functions. And I want to give a definition now. Okay, so here's the definition. F of n is big O of g of n if, in fact, it's if and only if, it's a definition, but if, since we haven't defined it yet, so let me write down if and only if. I can find two constants. If we can find, or there exist, and of course we could be using those symbols for there exist and for all and so on and so forth. But for now, let me not use those symbols. Let me write this down in words. If you're not super comfortable with those symbols, then it's just extra cognitive overload for using the symbols themselves. So I don't want to confuse the issue. So it's quite clear, and it's not that much more trouble to say this in words, that we can find two constants. These two constants will be called witnesses, constants, and we'll give them names C and K, such that f of n is less than or equal than this constant C times g of n, but not always. For all those n, for all n that are greater than this other constant K. That's what we mean by big O. And of course, if this is the first time you're seeing this definition, you will very understandably be forgiven to experience a slight sense of unease about this definition and a bit of bewilderment, because, what are these constants, C and K, if this is the first time you're seeing this? So it's okay if this right now, it doesn't make quite a lot of sense, but what we want to do as we go along is we'll do a bunch of examples, okay, today and next time. And every time we do an example, we'll be adapting this definition to the particular example, right? Now, I could have defined this completely differently. I could have used limits, for example, and it takes a minute or two to just give the definition. But let's just stick with the definition that we have right now on the screen. And then every time we see an example, and we'll start with an example in a second, we'll use this definition. What we'll be asked to do in each example is to, if we're asked to show this f of n, and we'll have concrete f of n, is big O of g of n, and we'll have a concrete g of n. If we're asked to show that, well, we are essentially, in effect, we're being asked to find these two constants, C and K, also called witnesses, for which this inequality holds. The C and K are called witnesses sometimes. Witnesses. What do they witness? They witness the fact that f of n is big O of g of n. That's what they're witnesses to. Now, before we go into the examples next, you can think of big O as less than or equal, but not less than or equal in the sense of arithmetic, like 5 is less than or equal. In some sense, it is less than or equal. It's less than or equal asymptotically. So every time you see big O, and I'll return to that point with the examples. Big O of g of n, when we say that f of n is big O of g of n, okay, we say that f of n in some sense is less than or equal than g of n. What is that sense in which f of n is smaller than g of n, not greater than g of n? In this sense that we have on the screen. Now, if it doesn't make sense,
When it's
yeah.
when it's not being divided by the constant. F
what do
of
you mean?
n, f of n would be less than or equal to g of n if
Mhm.
it was the constant times the function f of n instead of times g of n.
So let me understand what you just said. So f of n, you're saying that f of n would be less than or equal than g of n when? Again? If
Oh,
it,
never mind. I take it back. But I
no,
said
no.
if the constant was multiplied by f of n instead of divided.
Instead of divided. Okay. I'm not.
I was off a little bit.
No, it's okay. It's okay to be off. I'm just trying to determine what you had in mind, which, you know, that's exactly what we want to talk about, right? People's ideas, right? Because that's how we clarify this definition.
I have a question.
All the conceptions, misconceptions you can form about this definition. Of course, this will not be clear until we do like 25 examples. Yeah, and any other remarks?
Yeah, I have a question.
Yes.
These witnesses, like a C, has to be a positive number?
Yes. Yes, in our case, they will be positive numbers. C and K are strictly positive. In fact, well, K is greater than or equal to 0, but C is positive. So yes, that's a good point. If I were to give more strict definition, by the way, this definition also applies in a more general case for real functions. And there the definition can involve slightly more symbols. So for example, when the book gives a definition here somewhere, so you will have to deal with these modulus signs, the absolute value signs, and so on and so forth. This is a more general definition that accounts for negative values and so on. But C and K, yes, it is true that C is actually strictly positive. K can be 0, but usually it's that is the case. Yes, we want that in our definition above. And our definition, we want to simplify and they want to keep it this simple, because what we really do care about is only non-negative values for both the functions and the input values. And C and K will both be positive. Yes. Yes. That is.
Thank you.
Yeah.
So on conclusion, can we say if we consider this function as a big O notation, the function G of n, function G is, algorithm G is faster than algorithm F?
The other way. The other way. F is faster. F is faster. It's the
F
other
is
way. Yeah. Yeah. So yeah, good point. Yes, that's why we have it. But today we'll want to keep the discussion mathematical, right? So later we'll talk about the concrete algorithms behind these functions f of n. So f's and g's are these functions. So normally f will be something like, you know, in other books you will see t of n, the time it takes for an algorithm to run on an input of size n. In programming courses, you're most likely to see t of n instead of f.
And
g of n.
And that's the reason our witnesses cannot be the negative, because time cannot be the negative.
Yeah, yes. So if C were negative, for example, you're bounding the time from above by some non-negative function. If C were negative, that just doesn't make sense. This inequality does not hold. You're looking for that constant for which the equality holds, and that constant will have to be positive, in fact, not even non-negative. Right? Yeah, good point. Yeah, so that's exactly right. But our f of n, so normally, so since you brought this up, this f of n is the runtime of the algorithm. It's normally not a pretty looking function. So you implement a particular real world algorithm, you'll have like, I don't know, like just ugly looking function of some sort. And what you want to do is to somehow call that ugly looking function something much simpler. The whole idea of big O of n is to simplify the conversation about the runtimes of algorithms. So your g of n will be some simple looking function, like maybe some polynomial, like even like just n squared. Or so this g of n is normally something like n squared or n log n or something like that. And you want to say that your algorithm, whose actual real world runtime was some ugly looking expression like 3.71 n cubed plus 1 over 20 to the 7th power n log n, blah, 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 plus 22 point 85. So some ugly looking function. It's something you'd rather not deal with. That's the actual runtime, the actual in milliseconds. That's how long it takes, let's say. You want to simplify all of that fluff and say that this is roughly big O of n cubed, and that's it. That's one of the purposes of big O, to talk about complicated looking functions, unpleasant to deal with functions in a much simpler way, in a more elegant way. Does that make sense? But going back to your point, it's a good point. So so the point of you were making, yeah, yes, when you see big O, you're thinking less than or equal in some sense, right? So I did ask this question, and this is, by the way, it was like, maybe it was a trick question. This is what I want to sort of like you to have on the back of the mind, that when you see big O to be less than or equal. But we'll see what we mean by this kind of less than or equal as we go through the examples, right? So again, on one more side note, since we're at it, later we'll talk about big theta notation, big omega notation, and big O notation. So once we have big O down, these others will be just a breeze to like understand. Roughly, since we're at this topic, big O stands for less than or equal. Big omega stands greater than or equal in some sense, and the sense is asymptotic. And the theta will stand for just equality. Okay, so that's what it is. Okay. Okay, now I don't want to deviate even more. So let me just erase this because we could talk about this for a little bit. So let me erase. Yes, question, please.
One more question, yeah.
Yes.
It means like a fn n is going to be similar to g of n, right? Because c can be 1.
Yeah. Okay. Yeah. C can be 1.
Yeah. So we're talking about asymptotic functions, right?
Okay. So good point. Now, since we're at it, asymptotic. Now, we didn't talk about this when I first brought up these questions. When I asked you, what does it mean for two functions to be asymptotically equivalent? But here you have a function. Let's call it f of x. And g of x. When did you call them, just to be strict, like if you go back to calculus, you called them asymptotically equivalent. So what you did, you took the ratio of these functions, you let that x increase without bound. So you really considered the limit as x goes to infinity of the ratio of these two functions. And if that ratio, and someone brought this up, although we didn't write it down mathematically, if that ratio approaches not 1, but some constant number, it doesn't have to be a 1. I mean, it's neat, it's nice if it's a 1, but it's some constant number. Then we call these two functions equivalent in some sense, right? So this, if we had the notion of limit, like if we could rely on the notion of a limit, if we could define big O a little bit differently, it's still the same idea of big O, but we could define big O in terms of limits. And by the way, since we're at it, again, just historically, big O showed up by the end of the 19th century, and in number theory work by Bachmann first used it with limits. It's really also called Landau's symbol. Okay, so Landau used it in his work in the early 20th century, late 19th, early 20th century. And then Donald Knuth, everybody knows who Donald Knuth is, right? Donald Knuth brought it into computer science, and he was the one who introduced the notation for omega, theta, and big O. There's also small o and small omega notation for those who took real analysis, for example, know of those also. But okay, so since we're at it, those roughly correspond to strictly less and strictly greater. But let's leave that aside. That will take us far. Let's stick with the big O notation for now. Okay, so here's what any other remarks? Okay, so this is good point you brought up. This is asymptotic equivalence. This C doesn't have to be a 1. If it's a 1, if nice. In this case, we'll actually do examples where we fix C at 1 and see what happens to the other witness there, K, when you fix C. In fact, you can select one of the witnesses based on the other witness for big omega notation. For big omega, but big O, and it's slightly different for small o and small omega. But let's leave that aside. Let's stick with big O, what we have. Okay, so let me erase that. Let me actually copy this definition, because when we get to examples, okay, so we haven't had an example yet. So let's just do an example. At least 2 examples today. Okay, so here's the definition just to keep in mind. So that's the 0th question. We'll do example 1 in a minute. Just straight by applying the definition. Let's just do just this one only for now. Is 2n squared, this is my f of n. This is my function f of n. Big O of n cubed. This is my g of n. Notice that I've already begun to abuse the notation. I'm writing equality. This is not equality. Okay, we'll return to that. It's not equal. I should really, actually, since I haven't talked about this in detail, I should really say is, or a better way would be belongs, because it really, big O of g, it stands for a set of functions. But let's not further confuse this issue. Let's just stick with this definition here and say, is f of n big O of g of n? Big O of g of n. So my g of n is n cubed again, and my f of n is 2n squared. Just some functions. Is it, according to this definition? So in every instance that we'll do today and on Monday, we'll have our definition on the side. So it's when you do like 25 examples, you'll have the definition memorized. Okay, but you can't help but memorize that definition. For now, you might need to keep it on the side while you do the first 20 examples. So here it is, the definition. How does the definition apply here to this particular example?
Well, I would say that
Yes.
C has to be 1.
Okay.
And K has to be 2 and up.
Oh, okay. Good point. So, okay. So good, great. In fact, but okay. So, well, it doesn't have to be. Okay, I can nitpick. It doesn't have to be. You picked C equals 1. So let's pick C equals 1 for your suggestion here. The question is, what does K have to be? So what we want to have is, I want 2n squared to be less than or equal than C times g of n, which is n cubed. When will this hold? I mean, clearly when n is equal to 1, if n is 1, so if n is 1, then no way, it's not true, because I have 2n, okay, so 2n squared is not less than or equal than 1 squared. I'm sorry, 1 cubed. So it's not the case. So it's not less than or equal. So now you're maybe thinking, oh, you just told me you should be thinking of big O as less than or equal. Here's an example. No, it's not less than or equal. And you'd be right. But I said that you should think of big O as less than or equal in an asymptotic sense, in a very special sense, not just like, yes, this is true that f of n is not less than or equal than g of n here. But notice what happens as you've just suggested. When you picked C equals to 1 and the second witness K equals to 2, right? We always need a pair of witnesses. Okay, then so let me use a different color. So for those n's that are greater than or equal, in fact, that's what I used in the definition. Let's stick with greater than or equal. In the book, you see strict equality, but that turns out makes no difference. Greater than or equal K 2, which is, this is my K, and this is my C, just to be clear. Okay, when n is greater than that K, where K is 2, then for every n after that, n being 2, n being 3, n being 4, n being 50 gazillion, it is then true that 2 times 2 squared is less than or equal than 1 times n cubed, which is 2 cubed. So I fixed n at 2, okay? And then it is also true, so this is when n is 2, This is true when n is 3. Then I have the same thing. 2 times 3 squared is less than or equal than 1 times 2, I'm sorry, 3 cubed. 3 cubed. Okay, and maybe I should use here in red this 1. I want to use it in red, to put it in red, because that's the 1 that you've suggested there. Do you see that when I increase n now, that n becomes 4? What if n is 4? What happens then? Is it true still? And my question to you, right? So, oops, 4 cubed. In fact, the difference between the two diverges. Okay, there becomes bigger and bigger, the difference between these two. It's become, okay? So here's what's happening. If you want to draw a graph, here's what's happening. Here's n cubed. Here's n cubed function. And here's 2n squared. 2n, this is, has to be steeper. Okay, so maybe this is like that. Okay, so 2n squared. This is 2n squared. And this is up there, it's n cubed. Notice that, okay, so let me try it one more time. So let's say this is n cubed. So it starts off like this and then goes up. So this is like, the other side of it is like that, but we're not concerned about, we're just concerned about the first quadrant. So this is n cubed. Notice what's happening, that n cubed is always higher, it's above. That is the sense by which I said less than or equal. N cubed is always higher than 2n squared, but it's higher after a certain point, after some k. In fact, that k is not an integer here, but when this k is between 1 and 2. If k is 1, I'm right here. My n cubed is smaller. If k is 2, I'm right there. So this is the k. I should put it in red. Okay, this is the k that we selected was 2. At 2, n cubed. Oh, in fact, my cube. Oh, this is a nice example. This is even nicer than I thought. In fact, k is exactly 2. K is exactly 2. In the future example, it won't be exactly 2. In fact, k is exactly 2. K is exactly 2. At 2, these two lines intersect. 2n squared and n cubed intersect exactly at n equals 2. And when n becomes larger than 2, then n cubed dominates 2n squared, meaning that the 2n squared remains below n cubed for all those n's. So these are all these n's. And now these are all these n's. Here are all these n's, all these guys, ad infinitum. All these n's that are greater than or equal than 2, which is k. So all these greater than or equal than 2 n's. Does that make sense? So notice how we fit the definition to this particular example. Well, let's do one more. But does that make sense? I'll return to the other one later on Monday. Make sense, more or less? This is just only one example.
Yes, it makes sense, but I got a question.
Yeah, sure, please.
What's the answer to the first one?
To the first one, which one?
This one, 2n squared equal, it's a big O of n cube, cube. It's gonna be true or it's gonna be false. We gotta say it's true as long as c is equal to 1 or greater than 1 and k equals to 2 or greater than 2.
Good point. So the answer is true because true involves the entire definition with the whole enchilada of C's and K's and witnesses and the whole thing. This is the whole definition. So the whole, when I say, is this big O of something? Under big O, we understand the whole enchilada, right? Does that make sense?
No, not really.
No? Okay.
Yeah, okay. For me, it's okay. I mean, understand that, but when you say it's true for all the enchilada, it means like it's not true for k equal 1.
No. Well, what's not true for k equals 1 is this equality is not true. This equality is not big O. Big O involves this equality as part of it. The fact that 2n squared is big O of n cubed is a true statement as a proposition, as a logical proposition. It is true that the function 2n squared is big O of 3n cubed. That is a true statement.
Oh,
Now-
okay. So
Yes.
we're gonna say that it's true. It doesn't matter
true.
what value.
Yeah, no, it's just a true statement. Now, on the quiz or like on the test or something, you'll be asked to show why is it true? And then you will have to actually bring this definition into play and say, well, it is true that this is big O of this because I can show you the two constants, C and K, the so-called witnesses, for which this inequality will hold. And now you are talking about the explanation as to why in general, always, 2n squared is big O of n cubed. Does that make sense?
Now it makes sense.
Yeah, it makes it a little bit. So when the more you think about this, and this is like, so you think of it and you're like, as you're walking around like this, that's when you think about this. By the way, and also when you're socializing, when you're with your friends or your significant other and so on, you pretend to be doing these super important things like discussing your like relationships and so on. In reality, you're thinking mathematics in the back of your mind, and you're saying like, yeah, you're agreeing or doing whatever it takes, like to be agreeable. In reality, you're doing mathematics. Am I correct? And that's when the greatest ideas come to you, in the shower or during those conversations, right? That will happen. You try it and you'll see it will happen. Okay, anyway, all this aside, now we have to do more examples.
I have a
this is
que-
now recorded
que-
somewhere, so that's not good. Okay, yes, please.
For the first example, so on the conclusion, can we say like this? We have a two constant. Then on mathematically, if we're gonna add on the both side of equality, C and K constant, we can find some points that they can match with each other. We can
so-
catch the equality. So based on that, that will be true.
Okay, so now you're bringing up a very good point. I think now I'm not completely understanding you, but let me just answer you vaguely, and then when we do more examples, maybe you can bring up that point later too, right? And we can discuss it further. But the fact that we've shown the existence of this C and this K, right? Okay, that's just one pair of witnesses. In fact, we have an infinite number of witnesses for which this definition holds. So if I, for example, were to pick like C equals 10 in this example, my K didn't have to be as high as 2. It could have been smaller, right? So there is this interplay between the constants that's happening. You're adjusting the values of these constants. If you increase one, you can decrease the other, and so on and so forth. So let's see that play in the next example that's coming up, right? And in this one also we could, but let's just do another example. Since we are at 2166, we'll pick this example for f of x or f of n, whatever. Let's stick with f of x as 2x squared plus 16x. So sometimes I use n, sometimes x, it doesn't matter, plus 6, right? So let that be my f of n, f of x, okay, since I've used x already. And on the other hand, I'm gonna have g of x, and let g of x be x, how much time do we have? Then let's make it x to the 4th. Here's our definition. Here's our definition. Let me paste that. We need this definition here on top, just to have it here. So let's just see. The question is f of x big O of g of x? So is f of x big O of g of x? That's the question. Okay, so let's see. What do we need to do? Well, we need to find those constants C and K for which this definition holds. That's our goal in every question, in every big O question. Okay, so let's find out. Okay, this time, okay, it's like after this example, let's draw graphs, but let's do like this in a table that just this one time. What happens when x is 1? Well, here on this side, I have 2 times 1 squared plus 16 times 1 plus 6. Okay, this is going to be 24, right? So 22 and 2. On this side, I have 1 to the 4th, which is 1. The question is, it's not the case that this holds. It's not the case that this holds. 1 is not greater than or equal than 24. Okay, so I continue looking maybe for, so notice again, per the suggestion that came before, I fixed c equals to 1. This is what I'm doing, the bigger picture. I fixed my c equals to 1, and I'm looking for that k for which f of n for every, or f of x in this case. Okay, so f of x, for every x that is greater than k, that f of x is going to be smaller than 1 times g of x. Well, I'm saying here in the first line, I'm saying when x is 1, is it true that this inequality holds? Well, it's not true because 24 is not less than or equal than 1. Okay, well, maybe for higher values of x, it's going to be a little better. So let's try that. So how about let's try x equals 2. So with 2, I'm going to have 2 squared. So this is 8 plus 16 times 2 plus 6. Okay, so this is going to be 46, right? Is 46 less than or equal than 2 to the 4th, which is 16? The answer again is no, it's not. Okay, so you could draw the graphs and see, but before we draw the graphs, let's do it in a table, just this one more time. How about when x is 3? When x is 3, I'm talking about 3 squared plus 16 times 3, right? Plus 6, right? What do I get here? On the left-hand side, I have a 72. Is this less than or equal? This is on a question mark. 3 to the 4th. What is 3 to the 4th? I think it's 81. So at this point, I've hit the inequality. Do people see this? The inequality becomes true all of a sudden. And in fact, what's important, so here's my k, here's my cutoff point. So cutoff. K. This is my k. Or maybe we should have it in red because we have like these k's in this. This is my k. Okay, c was fixed at 1. C and k. So here's cutoff k. So when k became 3 or above, notice that for every x that's to come after that, let's do one more. So what we have is 4 squared plus 16 times 4 plus 6. That becomes 102. Is 102 less than or equal than 4 to the 4? You know 4 to the 4 to be 2 to the 8th, which is 2 to 56. You don't need to do much computation like this. So this is 256. Notice that the gap between 256 and 102 has just become larger than the gap between 72 and 81. In fact, if you go ahead and compute, I'm not going to compute this for x equals 5, but the gap will be even larger. In fact, we could compute it for x, but it's not too much computation, right? So 16 times 5, okay, so there's that 80. This is 50, right? And this is 6, right? So what's the answer here? 136. Okay, is it less than or equal than 5 to the 4th? Yeah. What is 5 to the 4th? Is it 625?
Yeah.
Okay, so that's 5 to the 4th. That's 25 squared. That's 625. The gap between these two is even larger. So if you wanted to draw a graph, and that's the best way to visualize it, really, I mean, not doing the tables all the time, is what we have here is that on the one hand, we have, okay, so I'm running out of space here, but okay, let's do it in a small place. So let's take this one. Let's do this one in purple. So I have some 2x squared. So this is my 2x squared plus 16x plus 6. And then I have this x cubed. X to the 4th. So x to the 4th is below it. Okay, this is my x to the 4th. But it grows much faster. The x to the 4th, its derivative is 4x cubed. Okay, the derivative of this function is 4x plus some like change, like 16. That's much smaller number. So, but at this point, the cutoff point, what's the cutoff point? It's somewhere below 3. This k here is really where they, if you just solve the calculus or pre-calculus problem, where do these two functions intersect? They would intersect at this point k. Where is that k? That k is between 2 and 3. Here's my 2, here's my 3. But for every x that is greater than that 3, that is for all these x's here, these all x's that are greater than or equal than 3, that's my k. For every x, it will be the case that x to the 4th will dominate this quadratic function. Does that make sense? So it's the best way to visualize this big O is to think of these like drawings of these functions. As one of you suggested at the very outset, the graph is a function. Yeah, it's a good way to think about it because we're visual beings. I mean, of course, there are functions we can't immediately visualize the graphs of, but we have software we can plot them if there's something too difficult. I mean, the basic functions, you should really know the plots of those in your mind. If there's something complicated, you can plot it in your favorite software, right?
I got a question.
Yes.
Okay, I got it. And of course, the first thing I will do if I do this kind of problems, I guess I'm gonna get the intersection point. So anyway, the thing is this: if I see I remember some mathematical functions where one of the functions becomes lower than the other function, they get the intersection point, but then over the time it comes back to the other way. So
yes,
there's only one small section where the big O will exist. So what happened with that?
Yes. So in that case, it will not be big O. So here's what you're suggesting. You're saying that this function is like below, then it goes above, and it seems to go above, but then at some point in the future does this weird thing where it becomes below again, right? Is that what you said?
Yeah, that's exactly.
Yeah. So then it's not, if this stays like that. So now let me ask you this. Good point. I'm glad you brought this up. Suppose, let's call this purple function. Actually, let's call this, just to confuse matters, let's call this guy g of x. And let's call the red function f of x. I gave them some random names. So suppose now that this pattern continues forever. That is, from this point on, and this is not quite answering your question, but I'll return to yours in a minute. Suppose that from this, let's call this n0 for whatever reason. From this n0 onward, like above here, f of x stays above. So question, is f of x big O of g of x? Is that true?
Yes, true, because if it's infinite, it's true. So infinite is bigger than that n number, right?
Yes.
Until that n0, the reverse, the g of x is bigger than fx, but after n0, fx bigger than gx. So it's true.
Okay, so
Right.
now, okay, so how about, is there a second opinion? Let me paste the definition here again.
Yeah, I got a second opinion.
Yes, please. What is it?
Because according to the definition,
Uh-huh.
it is always true that f of n is going to be lower or equal to c times g of n all the time after the first intersection point.
Yes.
So this one,
No, not the first
that's my question. This one is kind of, I think it's not.
Yeah, so actually it's after the last intersection point, but it is, so one of these two is correct. So here I've written down, if this pattern continues, if we agree that this pattern continues, right? If after this point f of x stays above, that one of these two is true. One of these two claims is true, and the other is false.
I think I could answer.
Yeah, which one is it?
I'd say g of x is O of f of x, but not the other way.
Yeah, yes, exactly. So now you're going back to that intuition I told about f of x. So big O of something, think of it, that's Simpson's cloud, I guess. I don't know what that came out to be, but so you get the idea. So big O of something. So big O of something. So f of x is larger than g of x. So g of x stays below. So g of x is big O of f of x. So this is true. So this is true. True is this one. The second one, true. The first one is false, right? So please don't confuse this on the exams, right? Right. So beginning at some point and onward, one of the functions should stay below. And the one that stays below is the smaller one. That's the guy on the left-hand side. That's the role in the definition that f plays. G is the bigger one.
So yeah, the times for gx is going down, but for fx is going up.
Yes, time for g of x, and this one is smaller than ffx's time.
Yeah. Well,
Right? So
I'm just confused about the convert, like thinking times. Otherwise, like I'm still thinking like what I said was right.
Yes, you had them confused. Otherwise, what you said is right. If you interchange the roles of f and g, you were correct. Right? Does that make sense? Right? So yes, that's absolutely right. Okay, so this is nowhere near enough. We need to see like tons more of these examples. Okay, let me stop the recording. I think we're a little bit over time. Did you guys sign in, or we didn't start the attendance?
No, we didn't.
Okay, so let's sign in right now. So I'm opening the attendance, so please sign in. It's open right now, so please check in. Please make sure that you check in. Okay, so please check in. All right, any questions? Let me stop the recording here, and I'll post this recording, I think, for all sections. We'll see how it goes. Where is this stop? I have to edit this, I guess, still. Okay.
I have a question.
Yeah, please.
For C, do you always just set it at equal to 1?
No.
Or no? It's just the examples we did?
Yeah, these are the examples. So now, good point. Since we're at this, suppose my C was 100 here. What would my NK be then? Suppose my C was 100. Does my K have to be as high as 3? So I'm adapting to this definition again. So now C, let's pick like some other color here. I don't know. Let's say this color. C is now 100. This change. What is, so this is C. What is the smallest K for which the definition holds?
Would that just be K equals 1?
Yeah, K equals 1 is enough, because for K1 and above, it's true that 100 times x to the 4th is going to be larger than this whole f, right? Does that make sense? Right?
Well, I see it this way. If we look for the intersection point of fx and gx, obviously fx, if we got a c x, we're going to say that the minimum, the turning back or the intersection point is going to be when x it's equal to fx. So the point of intersection going to be the 100, the c plus fx.
Can I, let me see if I understand you. When, so here's the picture, right, of the big O. So which one so this is the definition, again, same definition that we just gave with slightly, like, it's just only slightly different with a bit more complications here. But what we had is in our first, so in this case, f of x is big O of g of x. So here, this is the example where f of x, this f of x, the blue one, f of x, is big O of g of x. This is the definition of when that happens. Now, in our first example, our c was 1. So our c here was 1. And our intersection point here was about 2 or 3 or something like that. Let's say it was 3. So for every x above 3, that held. Now, the next question is, well, do you always pick c equals 1? Well, no. Now, suppose I increase c to 100. Can I ask you this question? What happens to c times g of x, like graphically? Graphically, if I make this 100,
faster.
Sorry, one more time.
It grows faster.
Yeah, it stretches. The growth rate is also faster. It's 100 times faster. Like the derivative just increase 100-fold too. That's true too. But it is of the same shape. It was a parabola. It's still a parabola, just with a different constant in front. But what happens is that because you shrink this, not shrink, but stretch the y-axis like 100 times, what happens is that this 100 times g of x now becomes a function that's like that. You stretched it. Do you see that this becomes much higher like that? The 100 times g of x is much higher. And then, and here's the point, your k just went from this k equaling 3 to a lower intersection point. K has just decreased from 3 to some lower number. Do you guys see that you have this freedom to play around to adjust the values of the witnesses of c and k? If I fixed c at 1, then this k worked, like that k between 2 and 3. I increased c, then a smaller k worked. And here's why it works. In terms of the picture, it's easier to imagine this, why this works. But algebraically also, if you start filling out those tables, then you'll see that if you fit like this 100 g of x, then the intersection point is just right there by 0. Right? Does that make sense?
Absolutely.
Okay. Yeah. So, okay. So we've just given a definition today. So next time we'll do more examples, right? So this big O should be like super duper clear. That's one of the aims of this class, is to make big O super duper clear, right? So that was just an introduction today. Now, please, by Monday, please read the entire chapter 3.2 and bring all the questions, suggestions. Like today, we had a nice conversation. People like gave suggestions. And so let's keep it that way, right? Now, again, it doesn't matter, right, wrong. We're having a discussion here. So please read chapter 3.2 and bring your comments, questions, whatever, next time on Monday, right? Make sense?
Yep.
Okay. Did everybody sign in? So let's end the check-in then. People sign in?
Yep.
Okay, so let's end the check-in, and it was good seeing you. Have a nice weekend, and please read chapter 3.2 by Monday. We'll have like tons of examples coming up on Monday. So I'll see you guys then, and we'll make those changes to the workflow of the quiz so that you don't have unnecessary aggravation during the quiz, like when to submit, where to upload, all that stuff. We'll fix that. Okay, so see you guys on Monday.
Thank you.
Okay, thank you. See you.